Hello. We are the authors of EVT, Efficient View Transformation for Multimodal 3D Object Detection. In this presentation, we will introduce our work on multimodal 3D object detection using LiDAR and camera sensors. The main focus of this paper is bird's-eye view fusion of these two modalities. Let's begin. Multimodal bird's-eye view fusion is crucial as it provides a consistent top-down representation of the environment. Cameras deliver dense semantic information, while LiDAR offers precise depth and geometric cues. Integrating these modalities in the BEV space leads to a more reliable perception, which is critical for tasks such as 3D object detection, BEV segmentation, 3D occupancy prediction, motion forecasting, and other downstream applications. The key and most challenging issue lies in transforming 2D image features into a BEV representation, in other words, addressing the problem of view transformation. There are two main approaches to view transformation, and the first is the depth-based method. In this approach, additional layers or networks are designed to estimate depth values or depth distributions directly from the image. The predicted per-pixel depth values or depth distributions are then used to lift 2D image features into 3D space along the camera rays. As a result, image features are projected into a continuous 3D volume. These features are then rasterized into voxel grids, and by applying pooling along the z-axis, a BEV feature map is finally obtained from the image. However, depth-based methods come with several limitations. First, the transformation process is highly sensitive to the accuracy of depth estimation. Predicting depth directly from an image is itself a very challenging task, and inevitably introduces significant errors. These inaccurate depth predictions directly degrade the overall performance of the model. Second, the resulting BEV feature maps tend to be extremely sparse. Since each image pixel can only be projected along its corresponding camera ray, a large portion of the 3D space remains unoccupied. This means that even regions where actual objects exist may fail to receive any features, leading to instability in the network. Third, when lifted features in 3D space are rasterized into voxel grids, the continuous values are quantized into discrete cells. This loss of precision reduces the representational capacity of the transformed features. Another major approach for view transformation is the query-based method. In this approach, a predefined 3D grid is used, and the center of each grid cell is projected onto the image plane to sample features. The sampled features are then assigned back to their corresponding voxel grid locations. To further enhance sampling quality, some methods employ a deformable attention mechanism, where offsets around the projected locations are introduced. Deformable attention iteratively updates these offsets through multiple sampling steps, expanding the receptive fields and enabling more effective feature sampling. Compared to depth-based methods, the output of query-based methods appears visually dense, since every 3D grid cell receives sampled features. However, this density is misleading. Even when a 3D grid cell corresponds to actual empty space, it is still projected onto the image plane and assigned with sampled features. As a result, the method copies irrelevant features into places where they do not belong, which can confuse the network. To mitigate this issue, deformable attention is often employed as mentioned earlier. Yet, iteratively adjusting sampling offsets is neither highly effective nor efficient, and in practice introduces significant computational bottlenecks. As discussed, both depth-based and query-based methods suffer from their own limitations. The resulting BEV feature maps often fail to clearly reflect what is actually captured by the sensors. This restricts the effective transfer of information throughout the network, highlighting the need for improvement. To address this issue, we propose a method that leverages LiDAR guidance to achieve noise-free and accurate transformations, producing dense BEV representations without introducing any computational bottlenecks. The proposed view transformation follows a two-stage strategy. In the first stage, adaptive sampling, an intermediate BEV feature map is generated from 2D image features. In the second stage, adaptive projection, this intermediate BEV feature map is further refined. The following slides will walk through each stage step by step. The first stage, adaptive sampling, generates an intermediate BEV feature map. This stage is similar to the query-based method introduced earlier. However, the key difference is that LiDAR guidance is used to adaptively sample 2D image features, ensuring that only features truly associated with the actual 3D space are selected. In more detail, in conventional query-based methods, image projection relies on predefined 3D grid points that are independent of the actual input. In contrast, our method leverages the LiDAR feature map. Through a simple layer, a fixed number of 3D points are generated along the z-axis for each BEV grid cell. These points are aligned with the 3D space actually occupied by objects, and they are indirectly supervised through the final 3D object detection loss. Unlike conventional query-based methods that place points at uniform intervals along the z-axis, this design allows the network to adaptively allocate denser points in regions where attention is needed, enabling a more flexible and effective representation. Next, the generated 3D sampling points are projected onto the image, and features are sampled using bilinear interpolation. In this process, deformable attention or other iterative refinement is not required. Since the sampling points are already well aligned with object regions as described in the previous slide, a single sampling step is sufficient to provide strong signals. This design is the key factor that makes our view transformation more efficient compared to previous approaches. The final step of adaptive sampling is to transform the floating point 3D image features into BEV form through weighted pooling. The weights are generated from the LiDAR features using a simple layer. Through this process, the adaptive sampling stage produces an intermediate BEV feature map from the image. Now let me explain the second stage, adaptive projection. Although the adaptive sampling module produces a BEV feature map with sufficiently strong signals, it inevitably contains a significant amount of noise. For example, as shown in the figure on the left, it is structurally difficult to suppress feature sampling in cases of occlusion or in empty 3D regions with no objects. Instead of spending additional effort on refining the camera ray transformation, we introduce the adaptive projection module as a second stage to refine the intermediate BEV feature map directly within the BEV space. The first step in adaptive projection is to generate pixel-wise refinement kernels from the LiDAR feature map. For example, if the channel dimension of the image bird's-eye view feature map is C, the module outputs a matrix of size C by C for each pixel. Next, the generated refinement kernels are applied to the intermediate BEV feature map through matrix multiplication. With LiDAR guidance, ambiguous or redundant features that are incorrectly transformed are suppressed. At the same time, features that align better with the actual 3D geometry are enhanced. Through this refinement, the final image-based BEV feature map is obtained. This refined BEV feature map can then be simply concatenated with the LiDAR features and used for a variety of 3D downstream tasks, including 3D object detection, BEV segmentation, and 3D occupancy prediction. Now I will move on to the results. As mentioned earlier, the adaptive sampling module generates points that are aligned with the 3D space actually occupied by objects. To verify this, we visualized the sampling points on image planes. In the top row, previous methods that rely on predefined 3D grid points often fail to capture object regions accurately. In the bottom row, our adaptive sampling points are consistently projected onto the areas where objects actually exist in the image, providing much stronger signals. This slide shows the visualization of the image BEV feature map obtained through the adaptive sampling and adaptive projection modules. Unlike the results from previous methods, these BEV features clearly reveal what scene the camera actually captured. Compared with the vanilla baseline, the adaptive sampling module produces stronger feature responses in the occupied regions. The adaptive projection module, on the other hand, effectively suppresses redundant features copied into empty space. Finally, when both AS and AP are applied together, redundant features are removed while the strong signals from the image are captured more effectively, which can be clearly observed in D. We evaluated our model on the new scenes validation and test sets. Under the same conditions, without model ensembling or test time augmentation, our method currently achieves the highest NDS among all existing models on the official new scenes leaderboard, which can be directly verified on the new scenes website. In addition, the speed test of our view transformation with ASAP shows a runtime of only 3 milliseconds, accounting for less than 2% of the overall model execution time. Compared with other state-of-the-art models, our method also achieves superior performance in terms of FPS. This concludes my presentation. Thank you for your attention.